Okay, my friends, this is going to be a very, very fun day for Roger. And what am I talking about? Well, physicists have finally figured out what we figured out years ago. Yes, Roger is in the brag mode today. Okay, my friends, vindication is sweet. Physicists found a way to trigger the strange glow of warp speed acceleration. The particles in the air glow when you accelerate through them. All right? Every time you take a step, space itself glows with a soft warmth. In other words, you are pushing and shoving the particles in front of you. Can we show that? Absolutely. So here is the soft glow of push to shove. Now, what is going on here? This is the pulsed red laser from a construction laser. This laser right here. Bip, 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 bip. Taken with a smartphone back in 2014, 2015. And I did all my work on this back then with Rod Warren. Now, this is light from this pulse laser coming forward, concussing with the gases that are in the air, causing those gases to become excited. Just like if you're walking through the air, they're going to get excited. You're never going to see them. They're not going to glow like this. No CMOS would pick up that much, not radiation. This is enormous radiation. And I can tell you what, the only reason we are seeing this tip glowing so brightly is that this is in the process of becoming accelerated. This would have normally just sort of gone pretty much like this. And I can show you those pictures, but this is the beginning phase of acceleration. And yes, we can accelerate light. All right, this is if it wasn't being accelerated. They're just coming forward. Now you see some of them glowing more than other areas. You see some of them going this way and some of them going that way, and some of them going basically straight. I can explain that too. All right, this is why we saw some going this way and some going that way. As light spins, and it spins, that is the spinning particle of light. After it went through the Venturis, and we're seeing the impression it makes. Some of them spin this, well, they're all spinning this way. It's a right-hand rule. This is nothing more than a drill bit. If you looked at it in a machinist, it's a drill bit, and it's screwing through this. So some of them are spinning off this way as they come over the top, and some of them are spinning off this way as they go through the bottom. And, you know, it's just the way it is. And the more they go right through the center, the more brilliant they are, because they are pushing each other harder. As they splay out, they get less and less push to shove. Simple as that. That's why we saw all those little spinning particles. Now, what happens when we hit the Venturi? This happens. Okay, let's go and remember that shot where it was showing all those spinning particles coming through, and they were all basically the same. Well, what happened here was this particular spot right here in line with the Venturi is apparently accelerating. It looks like to me. If you can claim that's not accelerating, I don't know exactly how. It appears to be accelerating, and the particle that was creating this wave, which I will show you in a moment, has extracted itself from its magnetic field, because the particle creates the field. The field pushes all these other particles. You see, those are still the same little glowy particles. Now they're really starting to glow. Now, remember I showed you that shower of all those red particles coming through, just thousands of them, and just spinning all basically the same way. Little ones, go back and remember and take a look. Those are these particles. You don't see those because they're not in line with the accelerator. They're just moving forward like they normally would. However, now with this explosion, which is fission, we divided the particles, and fusion, we have created literally a subatomic explosion, which illuminates the tips of all of these particles that were in the air, which we would never see before. But now they're radiating back at them, so it's push to shove. This is pushing, and these are trying to shove into them. You always get glow. Anytime you push and shove, you have glow, which is the glow of the background radiation they're talking about. We never see it. But that's what warms things up. If you go like through the air, you just warmed up the air. That's correct. Yeah, you just warmed up the air by pushing, and anything that pushes against anything else creates energy. E equals mc squared. Well, E is the energy, yes. The mass times the speed of light squared, all that stuff is nonsense. The mass depends on the weight of the particular object, whether it's a single particle or it's a 10-pounder, and then how fast it's going forward, and then what it concusses with, and then what the media is. So if it hits a real fluffy thing, you're going to get very little energetic value. If it hits some really hard thing, or bam, you're going to get a really whack, and that would drive something causing energy. If you hit a fluffy pillow, you don't create any energy, basically. You just go fluff. If you bang into a really hard nail and drive it into a board, well, you just created energy. So don't forget, this is what they would have looked like normally. The only reason this is glowing more than the rest is they're bashing into each other. There was a thing on he had the other day. I'm going to go and talk about it because he said, can light bump into each other? Absolutely. And when it does, it pushes and shoves and creates this particular line of interaction. You see them going this way and that way? That's because everything works with a right-hand rule. But we found a particle that went left-handed. That's whoa. Okay, my friends, I've watched this thing. This is Action Lab. He's very good, and I'm not trying to put him down. Here's what he has to. This is his question: can light bump into other light?
Hey everyone, today we're going to be seeing if light can actually bump into other light. I have two lasers here. Lasers concentrate a lot of light into...
Alright, he's going to show, and you can come up and watch this. I'll put a link to it. Can light bump into other light? Well, I showed it can, so that case is closed. Okay, they're trying to account for dark matter. Never going to be able to do it with the Bohr model. Impossible. It has to be the Dipole Electron Flood theory, which means everything is a dipole, and a proton is not made of one big gigantic positive. It's made out of 1,839 dipole, what we would have always called an electron. However, it's a dipole. It has a dark side, which is almost entire amount of matter. And they're talking about now, they know there's nothing correct about the Bohr model, but they're just trying to cling to it. This is how dark matter and regular matter talk to each other, claims Wild New Paper. And they're talking, our best guess about what dark matter might be is cold, I agree with that, weakly interacting massive particles. Massive particles, yes. Weakly interacting, no. Which experimental physicists around the world have been trying to detect for decades, but have not yet found. Well, we found them, I showed them. All right, here's another story right here. W boson breaking the standard model. Yes, I broke it long ago with Dr. Paul Sutter, and he's explaining this new announcement, and this is on Fraser Cain, and I would like to be part of this discussion. Now listen to this.
New result that was announced just, yesterday? 2 days ago?
Some point in the recent
past. Yeah. All right, so
I announced it 7 years ago.
Give you a chance to introduce yourself as well. Who are you? What do you do?
Hey, I am Dr. Paul Sutter. I am an astrophysicist and theoretical cosmologist at the Institute for Advanced Computational Science at Stony Brook University and a guest researcher at the Flatiron Institute in New York City. I am also the host of several TV shows and the author of a few books with more on the way, and I write articles all the time, including for the esteemed publication Universe Today.
Okay, I'd love to be part of the conversation. Why am I cut out of this? I don't have all those credentials. I don't need them. I can show, and then I would like to see what the response is. I'm not just coming up theoretically. That's the issue. I'm not a theoretical. I'm a material scientist. Always have been, always will be. And I always knew that the Bohr model did not work. No matter what calculations and mental gymnastics you went through, you just can't make it work. It never will. Here's another one, Fermilab. They're talking about neutrinos. How do particle accelerators make neutrinos? They smash things into little bits and then they dig through them. For 10 years, they've been digging through with 400 people looking for the particles. We can find scads of them. Okay, this could just be a coincidence. Like I say, I went to the University of Geneva for particle physics, and I mentioned this. We were doing this focused beam Venturi and separating the particles. I showed it to them, and they said, ooh, this is very interesting. You know, they didn't dismiss me at all, but they just never reacted other than have a nice day. So I went on my way, and I figured, well, I'll just keep showing it. Nobody would pay any attention. Now here they are. They went and reconfigured the Large Hadron Collider to focus the magnets to do the same thing we were doing. Over the past 3 years, the LHC team upgraded the magnet system to narrow the focus of the beams. Exactly what we did with our Venturi. So they can produce far more collisions. Well, they're still hitting head on, and they still have nothing but debris, and they still have no idea what that debris represents. And I think you saw Paul Sutter, within a day or two of firing it back up again, they see all the particles that we've been showing for many years. All right, Don Lincoln of Fermilab admits the whole space, no matter where you go, at the deepest part of space, you're going to be in this quantum foam. Quantum foam is nothing more than the particles I showed you. All right, let's just do a brief description of what is dark matter. It's a component of the universe whose presence is discerned. That means they can see it everywhere, they know it's everywhere, from its gravitational attraction rather than its luminosity. As we saw, the black didn't change size, it wouldn't go through the restriction. The white was very luminous, the black was just went around and reattached. And this is what we would see if we were in space and we had a heavy collection of matter. We could get charged particles. We would get a black hole in the middle. Can I prove that? Absolutely, I can prove that. And it makes up 99.5% of all the mass in the universe. And I can agree with that, because on a nuclear explosion, the first things it hits is the white particles, which they call the gamma radiation. Big deal. Call it anything you want. It's the white particles. They go flying. And those are the ones that burn. They don't concuss anything. And then after that, some black particles come from behind and smash everything to bits. I'm going to show you both of those events. The first thing I'm going to show you is a black hole in space the Russians created in 2015. You see that? That's the black hole the Russians created in space. They created a vacuum chamber, and then they injected charged particles into it. And they figured everyone was going to push every other guy away from itself and create a lattice inside there. Instead, it created a black hole. That is literally a black hole. Those are all charged particles surrounding that black hole, which is the dark matter and its gravity, because it's pulling all of those white particles in, and it doesn't mind being on top of itself. That is what gravity is. Okay, I've tried to get an audience with literally everybody. This is Veritasium. He's talking about, is the theory of electricity correct? When you turn on a switch, what actually happens? Well, first of all, I can tell you that nobody knows, because they don't understand. The Bohr model is wrong, and that what really happens is the dipole flood model. And I can explain electricity, I can explain sprites, I can elves and all of the different blue sprites and red sprites and all of the different interactions of our atmosphere, and why we're having global warming is because of the scrubbing through the particles that are in space. Space is not a vacuum. All right, so let's put it in a little bit of a package. Light, just normal light from a pulse red laser. And you can only photograph this in certain ways with the background, and Rod had all the ways of doing it correctly, and he's unbelievable work he did. Now, I did the same stuff, but not like Rod. I have exactly the same equipment he has there. And it goes back to 2014, a Galaxy S3 phone. Everything here was taken with a Galaxy S3 smartphone. And they say, yes, these things were fabulous for doing cosmic ray detection. All you need to do is get an energetic particle, and they had the CMOS ability to pick up these radiant energies and then separate them and then depixelate them so they're not squares. I had other people doing the same work, and they came up with all square blocks. Rod came up with all these, it came out of the phone like this. Now, again, this is coming forward and banging into just atmosphere, making it glow. That's the warmth of the glow of light. All right, that's all it is the glow of light. Sunlight is the same, only it has a whole batch of different colors, making it white, which interacts with every different gas in the air. I'm not sure what red interacts with. It might only interact with oxygen. I don't know. Who knows at this point? Now, you can clearly see that this is no longer just ambling along. It is, in my mind, accelerating. And then you can clearly see that there was other particles that were alongside this that we never saw because they didn't radiate. Now they're radiating because they're being pushed back, pushing and shoving, pushing, shoving, pushing. This is approximately, they say, if you can do what we did, and we did, is to separate the muons and the electron neutrinos here. That creates 200 times more energy. I say 207, I don't know, than when they were back here, just ambling along, just just barely pushing along. Everybody's happy. There's little dots are just glowing a little bit. Everybody's happy. Whoa, that changed right here. All bets are off now. Everybody is in chaos, and that is a subatomic explosion, literally. Fission and fusion. And what fizzed and fused? These particles. These are the particles. The black and white this is a muon neutrino, the black one. These are the electron neutrinos, the white ones. And what do electron neutrinos do? They glow. Those are the ones that are pushers and shovers. The black ones are just impactors. They have no glowy value. All right, let's talk about dark energy, because that's what they are. They're dark energy, they're muons, and they create gravity, and they are the pushers and shovers that force the white particles, which can compact, to squirt through here. The black particles cannot. You see the black ones here and the white ones? The black ones can't compact. Now, when it comes out of here, you get these Higgs fields, and they've been looking for those forever. Well, we found those way back to when, too. Now, here's the one I'm talking about, this crazy. Look at this thing. That one there. This one came back, I believe, backwards and hit one of the fields, the Higgs fields, and sloughed off that little particle. That changes a lot, I think. I don't know. At this point, there's a lot to look at. But we did what Fermilab and CERN wanted to do. Here it is right here. We separated the black from the white. And that's the muon neutrino separated from the electron neutrino, letting the muon go on by itself, the black ball, and the electron shower to create the electron shower. Then they fuse back together. So it's fission, fusion. I think we have extreme amounts of energy right there. And here's the particles actually that exist, that it is the particle. Here it is right here. Remember I showed you the black and white balls? That's it. That's a photon. Half of this is an electron, but it's still a dipole. We never knew about the black particle. Nobody knew about it. And there it is right there. This is this. Now this goes back to 2015. I did this about light is dark energy while traveling from the sun to the earth. This is nothing more than light, just like it comes from the sun. We know we're getting hit by sunlight. That's what these are. And in between, you don't see them. They don't even think they're there, but they are. These are particles, and they're everywhere, and they are pushing and shoving everywhere. And our outer atmosphere is scrubbing against these particles coming into our particles and creating our 2,700 degree outer atmosphere. Way out in the outer atmosphere, 2,007 degrees. Why? These scrub against, which is glued to our Earth, basically, our atmosphere. It's twirling and swirling, but it's still basically held to our globe by the pull of gravity, which is nothing more than the black particles. And they slam into that layer, causing extreme amounts of heat. And the same thing happens with the sun. As the sun spins through space, its corona is millions of degrees, its surface is only 1,000 or 10,000, because of the same reason. It's scrubbing through the particles it has to interact with. The arms of the Milky Way, they glow like hell because they're pushing and shoving everything that's in front of them. And then they create stripes in between them, which is the repulsion patterns, which is a separation of push to shove. Shown this very, very clearly, over and over and over, and since 2015. And it can't become any clearer than this. This is the fixed particle. This is like a bowling ball. It's a slammer. It does not compress, and it just weighs almost everything that this weighs. It's the black particles. Don Lincoln at Fermilab calls it a fixed particle. This is from an article he did. He shows, this is a picture I took right off of there. And this is the glowy particle. That's the same as we have, exactly. And these two create the spin. And you say, well, why does it spin? Well, remember as I showed you the wave going through the air, these are little particles right there that were being pushed to shove. Okay, I don't know if you can see them, But those are those little particles right in front that I showed before. No difference whatsoever. See those little particles? Now, what are they doing? They are charging up that electron neutrino. And when that electron neutrino charges up enough, it pushes it to the back. This one flops to the front. And they do it very, very quickly. They're bouncing. That's the muon wobble. And that makes a spin. So this one will go to the back. The bright one goes to the top. That's why they have up and down spin. This one's in the back. This one's just the top. When they see them just like this. Well, that's an upspin. Now, if this was over on this side, they'd make it all downspin. And this is a photon, not a quark or a lepton or all the other things they come up with. So we've seen the particles that Fermilab showed in 2013. They said we can see these particles. We know they're there. And that's about it they could do. Now, we see them too. But we could see them not by hitting things head on. We see the actual photons of light divided. So there is no mysterious digging through 10 years. They went, I think it's 10 years, and 400 people digging through these kind of events like this to find what we have right here. And they say, yeah, everything I'm saying, they can't dispute. Nobody's disputing it. They just won't confront it because they shut down for 3 years to make their heavy collider focus like we did. And I went to the University of Geneva back in 2015, I believe it was 2015, Coursera online, just to take a particle physics course there so that I could introduce this to them, and I did. And they said, ooh, that's very interesting, and that was the last I heard from them. And then shortly after that, they shut down their collider and made it focus into a beam like this. Only they're hitting still this way and this way head on. They're coming like this. We're forcing them to crush like this. They want to stick with the standard model. The standard model does not work. They can break their particles apart and see the same particles we see right here, the muon neutrino, electron neutrino. But they're digging through so much debris that all they can do is find bits and chunks. So instead of using a little particle like we used, the light, they're using big particles like this, hitting them head on. And now they're seeing all the light particles, yes. But then they're also seeing particles like this, and particles like that, and particles like this. They have no idea what they're seeing. That's why it took them 10 years digging through with 400 scientists to try to find this. I'm sorry, that's just a fact. Okay, they've been looking for new physics. I broke it long, long ago. Bohr model is no more. It never worked since I was in the Army. I knew this. I was in Nike Hercules missiles. I got out, and I fought like hell, and I fought the law, and the law won. But now the law has lost. I have won. Everything is a dipole. Everything there is. And they're all made of these two dipole particles. One is the muon neutrino, and one is the electron neutrino. We would call that an electron because nobody ever saw the dark matter before. That's dark matter. It's gravity. It's everything that nobody's ever known. And it's all the weight and the mass virtually of everything. All this does is burn. And this is the carrier. They're always talking about, well, we need a boson, we need a carrier. Well, there it is. And it carries that particle, and then they glue together just like bar magnets, exactly identical to bar magnets. And then when you put them in a mass, you get this. And the black can literally separate from the white. I showed this in my experiments. I just showed you, I think. Now, this is a cross-section of what a molecule or an atom or anything looks like, because we would never see inside to the dark matter. Never you could see that, because all the white particles want to get away from each other. They will always reside on the outside of the matter. And that's because the black particles don't mind being on top of each other. They have no problem with touching each other. The white particles say, get the hell away from me. And that's why when they come through the slit, they split out, and that's why that's the interference patterns they call it. Well, it's interference because of magnetism, not interference because they're flapping here and there because of two splits. We only have one slit. Now, let's see what they are claiming they just discovered. Okay, so let's calm down and read this through thoughtfully. This just came out today, 11th of May, 2022. Physicists found a way to trigger strange glow of warp speed acceleration. And don't forget, we saw those little particles glowing. But the only ones that were glowing were ones that were in this acceleration zone, where the other ones were pushing so hard that they forced them to glow, as you recall. All right, my friends, this is just unbelievable, because I can show you exactly what I have been saying in this picture right here. What are we looking at here? We're looking at particles that are coming straight forward, straight in line with the Venturi. Now, what are we seeing here? What the hell is going on with these things? And why are these laying flat like little Oreo cookies and these are sideways? And why did these particles just show up here and back here there's just nothing but dust? Why is there nothing here? Because these are the leading tips of all of the other particles that are here we never saw. The only one we see is the one that's directly in line with the Venturi, and then it explodes. It stacks up and causes this. It starts off as an Oreo cookie and then goes sideways just before it explodes. These are being pushed backwards. That's why they're straight up and down. That's the glow in the front of the waves of all of these. This one's being accelerated. And the same down here. The same things happen down below. Now, there appears to be some little misalignment of the Venturi. You see how these are sort of crazy looking down here, and these are a little different. And I see this the same thing with the green. Let me show you the green. But you can see the acceleration process. You see the division. You see there's nothing here. You never see those. That's why they say there's a very warm glow. Well, there's a glow that you cannot be seen until it goes into the acceleration phase, like they just said they just discovered. Well, we discovered it 7 years ago, at least. All right, I picked this up on the green, and this is the only one I have that is demonstrated. It's coming through spinning. They spin, as you saw. Now, what is happening here? It's basically doing the Cherenkov radiation thing, where it's coming and starting to slow down. Now, what's happened here? If you look real careful and you know how to understand what you're looking at, this had just flipped. This is more glowy than that, but it's going this way. That is just almost never seen, and the reason is it just flipped. This one now is going to begin to charge up, and there it is charged, and now it's going to flip, and that one will go to the front. You see how it's blurry here? It's the only one I caught with the blurriness during the flip. So this is my interpretation. I could be wrong, but it deserves to be looked at. It's coming through here, and again, the charged particle that was leading would have been this one, and it just finished charging up and flipping. Now the weak one has come to the front, and it's charging, and the next instant, I mean literal instant, it is fully charged and it's flipped. That's why you get all that spinning, wobbling so fast. Look at this. This is what it does. They spin and wobble. They know this, and I showed it. All right, this isn't long ago out. It's by Angela Nicoletti. 8 billion wobbling muons just put particle theory on notice. Well, everything I show put particle theory on notice long ago. Okay, my wonderful friends, I could do this all day. You know why? Because winning is fun. Now, what are we looking at? I'm sorry, I can't help myself. We're looking at this Higgs fields. Now, look at this. We can not only create the Higgs fields, we could crush them, just like the Feynman diagram showed, that you can crush particles and squirt them out. This is the particles just coming through the air. I've shown those very, very clearly. Acceleration, Higgs fields. And this literally is what these Higgs fields look like. They're, I don't know. That was done by Fabian. I had some very talented people working on this. So anyway, I'm going to leave it at that, and I just want you to know, 50 years ago, I not only did the theory, I did it, can you see this? Excuse me. I did all the calculations about energy and the heat of solution and all that different business and how energy was was drawn off of these materials depending upon how many electrons they had in them and their salt and acid contents and so forth. And it always ended up, everything was electric power. All right, everything, that's why batteries work. Anyway, it all ends up in electric power, even when you're working with fluids and so forth. So light is electric power, and here's what I said about light. Now this goes back 50 years ago, or actually more than that. Everything was dipole to dipole interactions, 100%. There was nothing other than that. And a transfer of energy is from light to atomic vapor. Absolutely correct. Light is nothing but little dipole particles. There they are. Okay, I'm going to call it quits for today here. I'm going to listen to a little bit of Queen. We are the champions, my friends. After 50 years, I hope this ends. Because science, they cannot defend. But I'd like them to try.